This presentation examines the two-sample z-test for proportions. First, we're going to establish when it's fair, and the two sets of data must come from simple random samples. If we are going to make some inferences about the entire population, we must make sure our samples were randomly chosen. Second, the sets must be independent. Third, there must be a large number of successes and a large number of failures in each set. 10 is a good number to aim for, but we are going to insist on having at least 5. So 5 successes and 5 failures in the first set, 5 successes and 5 failures in the second set. And finally, we want our population significantly larger than our sample. So we will insist that the population is at least 10 times as large as the sample we're working with. Here's some notation. P1 hat, number of successes divided by the total number in our first sample. P2 hat, number of successes divided by the total in the second sample. We also wanted to find P bar. P bar will be the overall number of successes divided by the overall total. So you'll notice I have number of successes in both samples divided by total number in both samples. How do we get that? Add the two numerators for the number of successes, add the two denominators for the total, and that's what we'll call an overall probability of success. And of course, Q bar, overall probability of failure. Q bar would be 1 minus P bar. So here's our null hypothesis and alternate hypothesis. P1 equals P2, which would mean that the two proportions come from populations with the same proportion. Or P1 greater than P2, the two samples come from populations where the first proportion is greater than the second proportion. Now, if we subtract P2 from both sides, we can rewrite H0 and HA. H0 P1 minus P2 equals 0 versus HA P1 minus P2 is greater than 0. And most statistics books require us to think about it from this perspective. Here's some data we're going to use. Our first sample of 100 items, we had 62 successes. Our second sample had 80 items, we had 44 successes. Can we conclude the first sample comes from a population with a larger overall proportion than does the second? So here's our formal test statistic. P1 hat minus P2 hat minus P1 minus P2 divided by the square root of P bar Q bar over N1 plus P bar Q bar over N2. We're going to make this a little bit simpler when we go back and look at our H0 and HA. Typically, H0 is going to be P1 minus P2 equals 0. If that's the case, I can simplify my test statistic and replace P1 minus P2 with 0. And then it gets a little bit simpler, and we have that as our test statistic. So that is what we are typically going to use. So there's our H0 and HA, and as well as our statistics, 62 out of 100, 44 out of 80. We want to figure out something about the parameters. So there is indeed our test statistic. So we're going to need to do what? I need to find out what P bar is. P bar, 62 plus 44, 106 over 100 plus 80, 180. And we get our P bar of 0.5889. And of course, Q bar will be 1 minus that. So Q bar is 0.4111. So making our substitutions, P1 hat, 62 over 100 will be 0.62. Will go in the first slot. P2 hat, 44 out of 80, works out to be 0.55, goes here. P bar Q bar, 0.5889, 0.4111, here, divided by N1, 100. P bar Q bar divided by N2. Now this is a very complicated computation. To do this, I am going to go to Excel. Okay, P1 hat is going to be the number of successes in the first trial divided by the total in the first trial. So we're going to say equal number of successes divided by total, and obviously we're going to get 0.62. P2 hat, using our second category, number of successes divided by the total, and there's our 0.55. To get P bar, we're going to add the numerators. Divided by, add the denominators. And what do we get? We get 0.5889. And of course, Q bar will be 1 minus P bar, will be 1 minus 0.5889. And we get 0.4111. Okay, here comes the difficult part. Z is going to equal parentheses P1 hat minus P2 hat divided by the square root of P bar Q bar over N1, P bar times Q bar over N1 plus P bar Q bar over N2, P bar times Q bar over N2, and this should give me my answer of 0.948. So our Z is 0.948. That's not a very extreme Z score, so that indicates to us now what will likely happen. So continuing, there's our H0, our HA. There is our other version of H0 and HA, and we have a Z of 0.948. This greater than sign tells me I have to shade to the right. So there is my Z. 0.948 is about there. My p-value is going to be defined by this area. It is a one-tailed test to the right. So I'm going to ask Minitab CDF 0.948 with a normal 0-1 distribution. What does that give me? It gives me 0.8284, so there's 82%, 83% or so of the area is to the left of the test statistic. So there's the 0.8284. So the amount to the right, of course, is just 1 minus that, or 0.1716, and that, of course, is my p-value. So assuming these two samples came from populations with equal proportions, the chances of getting numbers this different just by random chance is 17%, and that's fairly high. So essentially we have to recognize the fact that H0 could be true. We don't have enough evidence to throw it out. We have to retain H0 as possible. So indeed, our p-value is 0.1716. Since the p-value is large, we fail to reject H0. So we do not have enough evidence to conclude that the first sample comes from a population with a greater proportion than the second. They may be the same. We don't know. Okay, here's one more example. This time it'll be a two-tailed test. H0 P1 equals P2. Subtracting the P2, we get P1 minus P2 is 0. Versus HA P1 does not equal P2, or P1 minus P2 does not equal 0. And this time we have 34 out of 200 in our first sample and 28 out of 100 in our second sample. And the question we ask is, do these samples come from populations with differing overall proportions? So again, there's our test statistic, and P1 minus P2, again, we're going to assume is 0. So we'll work off of this version of the test statistic. So there's our information, and there is our test statistic. We want P bar, 34 plus 28, over 200 plus 100. Total number of successes, 62. Total number of trials, 300. P bar is 0.2067. Q bar is 1 minus P bar, 1 minus 0.2067, or 0.7933. And now we have to do our work. P1 hat, 34 over 200, is 17%, minus P2 hat, 28 over 100, of course, is 0.28. And we will go ahead and again do this computation using Excel. First off, 34 out of 200, 34 successes out of 200 total for group 1. And then we have 28 out of 100 for group 2. 28 out of 100. And you'll notice I've done all of the spreadsheet programming on the last example, and it gives me my Z of negative 2.218, also gives me P1 hat, P2 hat, and P bar, Q bar. But most importantly, I now have my test statistic Z, negative 2.218. This is a much more extreme Z score than we had in the first example. Notice this is a two-tailed test. P1 does not equal P2. So again, our null hypotheses, alternate hypotheses, and our Z-score. Negative 2.218 on the left side, negative 2.218 on the right side, two-tailed test. We're going to ask Minitab to do CDF negative 2.218. It is a Z, so it's normal 0, 1, period. Should be there. then what does that give us? That gives us 0.01327774, so 0133 in this tail, 0133 in that tail. So we get a p-value of 0.0266. Now if the p-value is 0.0266, what does that tell us? Since the p-value is small, we have to reject h0. We throw h0 out, which means we have evidence of HA. So how will we state that conclusion? We have sufficient evidence to conclude that the first sample comes from a population with a different proportion than does the second. And that will conclude this presentation.